Assalamu alaikum, sabah khair jami'an. I hope my voice is clear. Can you just tell me in the chat or open your mics and just tell me if my voice is not like cutting off or anything like that?
It's clear.
Thank you. So my name is Renad. I'm a fifth year. Today I'm going to give you an overview of the autonomic nervous system, particularly the sympathetic and parasympathetic divisions, which are the main divisions of it. I think before we start, that you have to understand the importance of this topic for you in this course and later on during your medical school journey. The autonomic nervous system and the effects of both the parasympathetic and the sympathetic systems on the body explain a lot of how drugs work or the mechanism of actions of a lot of drugs. So it will help you in understanding pharma. And also it can explain the symptomology of various diseases and conditions. So that will help you also understand the pathophysiology and how each disease or illness manifests. So saying all that, I don't want to make this a long lecture, so we'll go on and start. First, I'm going to start with the basic organization that Yazid, Allah Ta'ala, just explained. The nervous system is divided into central and peripheral. The central nervous system is the brain and the spinal cord. The peripheral is considered from the physiological point of view to be divided into motor and sensory neurons. So you can say in different words that the peripheral nervous system is kind of like the conduction pathway to and from the central nervous system. So sensory neurons conduct sensations or impulses from the organs towards the CNS, and the motor neurons conduct the motor or efferent impulses from the CNS to the effector organs. Here, our concentration today is going to be on the motor neurons, which are divided further into somatic, which control voluntary movements like the movements of skeletal muscles and what like, and the autonomic nervous system, which is our focus for today, which controls involuntary responses, reflexes, internal organs, viscera, and the like. It's divided into sympathetic and parasympathetic divisions. Each of them has a certain role that it plays in the body, and that's where the importance of understanding their jobs and function lies. The sympathetic is called fight or flight. The parasympathetic is rest and digest, depending on the jobs or functions of each. Now, as I said, that the autonomic nervous system controls visceral or involuntary functions of the body. So it can be considered the motor system of visceral organs, blood vessels, and glands. Its central portions are located in the hypothalamus, brainstem, and the spinal cord. And you can see here that the cerebral cortex and the limbic cortex can influence the actions of the autonomic nervous system, but they do not directly affect it or control it. And that gives the reflexes that the autonomic nervous system produces speed and rapidity. So, as I said, it operates through visceral reflexes, where sensory signals arrive from the organs or viscera to the autonomic ganglia, the hypothalamus, or the brainstem. Then they're processed and returned as reflex responses that are subconscious towards these organs to control the actions. So now that we've known the general function of the autonomic nervous system, we should know the basic anatomy of it. Here you can see that something is very special here to the anatomy of the autonomic nervous system, wherein there are two, not one neurons in the chain of command. It's called a two-neuron chain of command, wherein the first neuron, called a preganglionic neuron, referencing the autonomic ganglion, that the preganglionic and postganglionic neurons synapse in. So here you can see that the first neuron starts in the spinal cord and its cell body lies there. And then its axon leaves through the ventral root towards the autonomic ganglion, where another cell body or a neuronal body lies and it synapses with it. And then the postganglionic neuron its axon leaves towards the so as you can see here, the preganglionic neuron is myelinated, meaning it has a certain sheath that covers the axon, lending the impulse's speed in reaching their effector or the organ that it wants to reach. But the postganglionic neuron is not myelinated, and that leads to a decrease in speed. But you should know that unmyelinated axons are more metabolically active, and that lends validity, or it betters the actions of this neuron or axon on the effector organs. So here is the basic anatomy. In the sympathetic and the parasympathetic systems, there are slight differences between them depending on the functions that they both carry in the body, and we'll soon see the difference. Here you can see that the somatic nervous system, there is a single neuron, unlike the sympathetic and parasympathetic divisions of the autonomic, where are two neurons. So voluntary actions are controlled by one neuron only, but the involuntary ones are controlled by two, or a chain of two. So you can see here in the sympathetic, the preganglionic axon or neuron is very, very short compared to the axon of the postganglionic. And here, the ganglion of the sympathetic nervous system is very much closer to the CNS than the ganglion of the parasympathetic. Here, and it lends it its name, a paravertebral or prevertebral ganglion. But seeing here in the parasympathetic nervous system, the preganglionic axon is long, but the postganglionic axon is short, and the ganglion is closer, or a lot of times is on the wall of the organ that it affects. And it's called here, for that reason, a terminal ganglion. Going through here, I'm going to talk about the important distinctions between the sympathetic nervous system and the parasympathetic ones in terms of anatomy. Here we can see that preganglionic sympathetic neurons originate from the lateral horns, as you can see here, these little ones at the sides, in the levels T1 to L2, which is the thoracolumbar segments of the spinal cord, and they leave it through the ventral roots, as we've seen before, and they enter the sympathetic chain, which is a chain of autonomic ganglia very close to the vertebra. And as I've said before, the preganglionic neurons or axons are short and lightly myelinated, while the postganglionic ones are long and unmyelinated. The axons are highly branched, so they can control here, like the first ones, they can control multiple or synapse with multiple autonomic ganglia, leading to more universal effect to be conducted on the organs. And here there's a certain distinction or an exception to the rule of the sympathetic neurons, preganglionic ones, synapsing with autonomic ganglia in the case of the adrenal medulla. The preganglionic nerve fibers just pass all the way to the adrenal medulla without synapsing with an autonomic ganglia. And there's a certain like explanation where from an embryological point of view, the adrenal medulla is similar to neural tissue. So there is no need for the passage, or it explains why there is no synapsing with the autonomic ganglia. So going through with the parasympathetic part, the preganglionic parasympathetic neurons originate from either brainstem nuclei, and that is important in the actions of the parasympathetic nervous system, and it explains them, or in the sacral spinal cord segments 2 to 4, so S2 to S4. Their axons leave the brain or the brainstem via cranial nerves 3, 7, 9, and 70% of them, so mainly 10. So 3 is the oculomotor. You'll soon, in the CNS block or throughout this course, you'll know each function of each cranial nerve. So number 3 is an oculomotor nerve. Oculo, which means eye, motor, which means movement. So it's considered, or it affects the movements of the eye. Number 7, which is the facial. Number 9, glossopharyngeal, and the 10th, which is the vagus. And the 10th one, vagus, it affects the heart, the lung, most of the GI tract. So a lot of the effects of the parasympathetic nervous system is conducted by the vagus nerve. And that explains why a lot of their axons, or 75, leave through it. Or from the sacral spinal cord segments, it leaves through the pelvic nerves, and it affects the bladder, for instance, the rectum, and the lower parts of the colon. Here, as I said before, the preganglionic neurons are long and myelinated, while the postganglionic are short and unmyelinated. Their axons have few branches, which differs from the sympathetic, which is highly branched, and the ganglia are close to or on the target organs themselves. So that's another difference. Now, since we've know now the anatomy or basic anatomy of the autonomic nervous system, we'll go on to the neurotransmitters that affect this system. We know that there are a lot of neurotransmitters, and each has its own importance and its own function in the CNS. But in the case of the autonomic nervous system, there are two main neurotransmitters, one called acetylcholine, and the other one is called norepinephrine. The neurons in the ANS are divided into two based on the type of neurotransmitters that it releases. So you can see here that the acetylcholine releasing neurons are called cholinergic, while the ones that release norepinephrine are adrenergic. There are certain basic points that you should know and keep in mind, that all preganglionic neurons, whether sympathetic or parasympathetic, are cholinergic, so they release acetylcholine, and all parasympathetic postganglionic are cholinergic. So the parasympathetic chain is all controlled with acetylcholine or cholinergic neurons, while most of the sympathetic postganglionic are adrenergic, releasing norepinephrine, except a certain exception, like nerve fibers to the sweat glands or some blood vessels, which are cholinergic. So in general, parasympathetic is all cholinergic. The sympathetic is cholinergic preganglionic, adrenergic postganglionic, with a certain exception of the sweat glands. Now, since we know the neurotransmitters, we have to know the receptors that these neurotransmitters attach to and exert their functions on. There are two types of receptors, as we said before, like the neurons divided into two based on the neurotransmitter. cholinergic receptors, which are muscarinic and nicotinic, adrenergic receptors, which are alpha and beta. There are certain types of alpha, 1 or 2, beta, 1, 2, 3, and each has its function. So this is a very important piece of information to keep in mind, that the effect of the postganglionic sympathetic fibers is determined by the type of receptor to which it binds, not the type of organ, and nothing other than the type of receptor to which it binds. So you can see here the type of receptors. The somatic is controlled by the nicotinic receptor. Here, all the preganglionic receptors are nicotinic, as you can see. As we've said before, all of them, or the preganglionic, whether sympathetic or parasympathetic, is cholinergic, and you can see here why. And in the sympathetic, the postganglionic ones that are adrenergic are alpha and beta, while the ones in the sweat glands, which is controlled by acetylcholine, is muscarinic, not nicotinic. The parasympathetic postganglionic is also muscarinic. And as we've said, the adrenal medulla is directly synapsing with the preganglionic sympathetic neuron, and it's controlled by the nicotinic receptor. You can see here, repeating, that all the preganglionic are nicotinic receptors, the postganglionic cholinergic are muscarinic, while the adrenergic are alpha and beta. Here you can see that the sympathetic is called fight or flight, and the parasympathetic is rest and digest. That shows what each of them, or what effect each of them conveys or lends to the body. Here, you know that a certain balance should be reached in everything in the body to achieve a certain ultimate function. So there is a certain basal tone of the sympathetic and the parasympathetic that work together to reach an equilibrium in where the body can function in the most effective and efficient way. So going on now, since we've went through the anatomy, neurotransmitters, and receptors, we should go towards the functions of each. Here is the thing that you should know to understand the effects of the drugs in pharma, as we said before, and the certain manifestations of some diseases. So going through the table, the eye here, where the effect of the sympathetic stimulation, the pupil is dilated to allow more light to enter the eye, and that can help in stressful situations. Ciliary muscles, which control the lens, leading to its control of accommodation, is slightly relaxed, so more far vision, and it helps also in these stressful situations. While in the parasympathetic, the pupils are constricted and the ciliary muscles are constricted, so more near vision. The glands here, all, whether nasal, lacrimal, parotid, submandibular, gastric, or pancreatic, all secretory glands of the body, are affected by the sympathetic stimulation indirectly through vasoconstriction. So blood vessels are constricted, less blood reaches those glands, leading to decreased secretion. But in the parasympathetic part, it directly stimulates those glands to release secretions. But on the other hand, in the sympathetic nervous system, it affects the sweat glands, as we've seen before, directly. So there is an increased sweating, where in the parasympathetic, there's sweating not directly contribute to the sweat glands release. Apocrine glands, which are glands that can be found in the underarms, the effect of the sympathetic stimulation is for it to release a thick secretion that has a certain odor to it, while the effect of the parasympathetic is non-existent on the apocrine glands. The blood vessels in the sympathetic point of view is constricted, while in the parasympathetic, there are usually no effect. The heart muscles, which is very important thing to notice here, in the sympathetic, as we've seen that, as we've said before, that it acts upon a stressful situation. So in times of stress, you need more blood pumped into the body. So there's an increased contractility or force of contraction of the heart muscle, and there's an increased rate, so an increased cardiac output. The coronary arteries differ depending on the type of receptor that the adrenergic neurotransmitters act upon, whether by beta 2, which is dilated, alpha, which is constricted. So that highlights the point that I've said before, that the type or the effect of the postganglionic sympathetic neurons depend on the receptor that it acts upon or attaches to, not to the organ, since here you can see that it differs in a single organ. In the parasympathetic stimulation, since it acts more in peaceful or relaxed situations, there is no need for the heart, there's no need for an increased cardiac output, so the muscles are slowed in rate or decreased in contractility, and the coronaries are dilated, so more blood gets to the heart muscle. Going into the lungs, the bronchi are dilated and the blood vessels are constricted, where in the parasympathetic, the bronchi are constricted and the blood vessels are dilated. Here in the sympathetic stimulation, the bronchi are dilated to allow more air entry into the lungs, leading to increased gas exchange, meaning more oxygen getting into the blood. And that also helps in the process of the stress response. Here, the gut, where the most of the parasympathetic action is highlighted. You can see here in the parasympathetic stimulation, there is an increased peristalsis and tone, and the sphincters are relaxed. So more absorption of nutrients, more movements and digestion of foodstuff and what like. While in the sympathetic, you can see there's a decrease in peristalsis and tone, and there's an increased tone in sphincters. Here you can see that the gut or the absorption of nutrients is not very important in the case of a stressful situation or fight or flight. So mostly the blood is shunted towards the skeletal muscles, the heart, things that are important or critical for rapid response, and not the gut, which is not critical. So going more, here in the liver, in the sympathetic, glucose is released. And as you've known that glucose is very important in the production of ATP, which is the energy used by the cells to release or function in general. So it is very important for the body to have enough glucose to conduct its functions in stressful situations. While in the parasympathetic, there is a glycogen synthesis because the body does not need excess glucose in the blood, where it is in a peaceful or a relaxed situation. So glycogen is synthesized and stored in the liver. Here, the gallbladder and the bile ducts are relaxed in the sympathetic part, while in the parasympathetic is contracted. Here also, similar to the gut, the kidney, there's a decreased urine output and increased renal secretion. Why? Because as we've said before, that the blood vessels are constricted. So there's decreased blood flow into the kidneys, leading to a decreased urine production and decreased urine output. And since there's an increased renin secretion, it might also contribute to the vasoconstriction uh, uh, that the sympathetic system uh, achieves. But there is no effect of the parasympathetic system on the kidneys. In the bladder, you can see that the detrusor muscle is relaxed in the sympathetic while the trigon is contracted, and the opposite in the parasympathetic. You can see here that the parasympathetic effect on the male genitalia is erection, while in the sympathetic one is ejaculation. The systemic arterioles here depends upon the type of receptor that the body or the act upon. Where abdominal viscera, it's constricted. The muscle depends whether alpha, beta, or cholinergic, and it differs in the action, while skin is constricted since it's not important in the stress response. But the parasympathetic has no effect. In the blood, you can see here that lipids and glucose are increased in the case of sympathetic, leading to increased energy production. The coagulation is also increased, while the parasympathetic has no function in here. Basal metabolism, as we've said before, energy production and what the like, is increased up to 100% in the sympathetic system or stress response. Adrenal medullary secretion is increased in the sympathetic, while there's no effect to the parasympathetic, as we've seen that the adrenal medulla is not supplied by the parasympathetic system, so there's no action to it. Mental activity is increased, and that's very important since when a person or a being is in a very stressful situation or a fearful situation, mental activity is highly desirable, you can say. So it's important that it's increased. The piloerector muscles here are the muscles that are attached to the hair follicle. So you can see sometimes that when you're stressed or you're afraid or something like that, you get goosebumps. And that means that the piloerector muscle is contracted, and that's the action of the sympathetic. Skeletal muscles, there is increased glycogenolysis for glucose release and increased strength. Fat cells, there's a lipolysis for increased metabolism and energy production, while no effects of the parasympathetic system is seen here. So since we went through the actions, there are a lot of actions of these or effects of either the parasympathetic or the sympathetic that are very minute, you can say, but there are very important ones that you should keep in mind, like its effect on the eyes, for the drugs that affect the eyes, for instance, the heart, which is very important since, and the lungs also, since it can be of use to you in the future. So just keep in mind the most important ones, and the others, once you know why each of the sympathetic and the parasympathetic systems work, you can deduce how the effect of each of them on this certain organ. So once you know that the sympathetic favors important or critical function, you'll know which ones are critical or not. And the parasympathetic, since it works in peaceful times, you'll know what it wouldn't or it would affect. So here I've put a few tables that are very useful and helpful. Here are the differences between the sympathetic and parasympathetic divisions compared to the somatic nervous system. We went through all of these throughout this lecture, but here it's lovely and concise, and you can go through them to just like solidify the facts in your brain. And here are the adrenergic receptors and functions of each. As I've said before, the sympathetic function depends on the type of receptor that the neurotransmitter acts upon. So here you can see the difference between the alpha and the beta, and it's a nice thing to keep in mind. This is it. Thank you very much for listening. I hope you've enjoyed the lecture, and I hope that I didn't give you too much to think about today. My references are Guyton and Hall textbook and The Physiology by Linda Costanzo. I have a certain thing to say. If you feel that you're kind of lost throughout physiology, I'd recommend going through the pocket version of the Guyton and Hall. It's very nice, very concise. You can go through it very fast before reading more in depth into what topic you want. And inshallah, you'll understand it in the future. Is there any questions on anything, whether on the blog or the lecture itself? I'll be happy to answer.
Thank you so much, Renad. You were incredible. If anyone has any questions,
thank you.
Please ask right now.
I have a question.
No problem, go on.
What's the difference between the sweat glands and the apocrine?
There is a different function in each of them. The sweat glands release a more, you can say, a less viscous type of fluid than in the apocrine glands. And the apocrine glands are more controlled by, you can say, sex-related hormones like testosterone and what the like, wherein sweat glands are not controlled by it. So it differs mostly in the where in the body they're located, since apocrine glands are not found all over the body. It's found in certain parts like the genitalia and under the arms, while sweat glands can be found all over the body. And the type of fluid it releases and the what affects them to release the type of fluids they release. So that's the main difference between them.
Thank you so much.
No problem.